Hey guys, I've got two electrical problems on my house that could kill me. Now, something tells me that these are not uncommon. So let's go ahead and get started. So in order for me to explain these electrical problems, really you kind of need to know how electricity works in your house and how like the grounding works. Now I know there are a lot of videos that kind of go quickly on how the ground works in your house purpose, but I thought I'd have a discussion with my wife and show her how everything works in the house and really the purpose of the ground and how it should keep you safe. But if you are familiar with, the purpose of ground, purpose of a ground neutral connection bond, feel free to skip ahead to this timestamp and then you can see, what I did to make my house safer and the issue that I was having in my house. Now, this is just going to be the first video on the subject because I have additional problems with my house that make my house kind of dangerous. So I'm going to have a second video on this as well. And of course, I know this is a solar channel specifically, but if you have problems with your home electrical system, you want to fix those before you connect all of your expensive solar equipment to your house because it might screw up your equipment. So I know in this next section we don't have microphones, so hang in there. I think you can hear everything, and I've tried to edit things down to be as concise as possible. Okay, this is going to be a little bit different video here today because I've got a special guest here, my wife. She's on the other side of the camera, but I want to make sure, this is such an important concept, knowing about ground and how to keep yourself safe in your home and make sure that your appliances are safe and your outlets are safe and all your wiring is safe. So one thing that's super important is knowing about your ground neutral bond. That's very important to have in your house. And so here's our lovely green grass here, and there's power lines, right? So we're just going to do a little power line here. All right, and here on the power line, we've got this little transformer here, this box. You've probably seen those on the side of the wires will come into the box, and here's a transformer. It's a little, looks kind of like a battery actually, on the side of the power line. And here is our house. Here. And from the power line, we have power that comes over to our house. I'll just do dotted line for hot. So it comes over to our house, goes through the electrical meter, and we have also a shut-off switch on the side of our house. It goes through that, and then eventually it goes over to an electrical panel. At the top of the electrical panel, we have this big shut-off switch here. And we have big terminals at the shut-off switch.
So is that red line, that line that connects to the house, is that under the ground, or is that like actual line that's connected?
Depends on where you are, but for sometimes there's power that comes into the top of your house. There's like a little weatherhead where the power goes in. Mm-hmm. For our specific house, it's like under the ground. Okay. But for this discussion, I'm just going to draw it above the ground because I think a lot of people have it above the ground. Mm-hmm. But say whether it's coming above the ground, it is still coming into your house and it's going through your electrical meter. And we have a shut-off switch. Not everyone has a shut-off switch inside the house. Okay. But I'll just do the red line and a dotted line. So that's like the hot. Now I know there's alternating current and DC current. Mm-hmm. DC current is one way, but alternating current kind of goes back and forth. Okay. But for this discussion, we're just going to assume the power's all going in one way just because it's easier to explain. Okay. It's more of the concept is the same. Okay. Either way. So we're just going to assume the power's all going in one direction. And so here, now there's also more hotlines, but we're just going to say there's just one hotline for now because there's multiple hotlines, but we're just going to discuss one hotline to make this as simple as possible. So there's one hotline that comes in, and then power needs to go back out to where it comes from. So similar to like a school science experiment, you have your battery. Mm-hmm. I don't know if you've seen this, and then like the little kid has like a little light bulb, and then it goes to like a switch, and then it comes back. Yeah, I've seen this. Yeah, so power really needs to go complete the circuit. The light bulb isn't on unless like he closes the switch, and then he closes the switch, and then you complete the circuit.
Okay.
So power really needs to go back to where it came from for the current to power any devices.
Okay.
So this, you can think of this little transformer as kind of like the battery. So power needs to come back into the transformer or back to its source. So this is the neutral. This is usually a white wire, but I'm just gonna show it in blue because white wouldn't show up very good
Yeah.
on the chalkboard. So here's the white wire. So it comes over through the house as well, and it'll land on this bus bar. So it's just a metal bar that is inside our metal electrical panel. And this bus bar, there's like some screws in there where you screw all of the neutrals on. So this is the hot and this is the neutral. And this bus bar is not connected to the metal frame of the electrical panel either. That's important to know. So from here, so we have power coming in. So let's then also below this, we have a bunch of breakers that'll feed different circuits in our house. If you're running like a whole bunch of appliances in your house, sometimes your breaker will flip and then you just switch it back. Here's the little switch. This circuit right here, the top circuit, you have a lot of these circuits. This top circuit, you know, it comes through, power comes through here, comes through this bus bar and it goes through this breaker. And we'll say it goes over to a light.
Like that particular breaker just powers that light.
Yeah, we'll just say it just powers just one light.
Okay.
One light for now. So here's our light. Here's our light bulb. And then we got an old house, so we'll just say there's like a little tiny old wire that goes in here, that little filament comes down, and then the wire from the filament comes down here and pokes out the bottom. And so we need to connect our hot wire on here. And right now, is the light bulb on?
No, you haven't turned it on, right? Or have you turned it
well,
on?
we'll say we don't have any light switches in the house.
Oh,
So
okay.
there's no light switches, it's just a connection. So it's not going to turn on unless, just like you have a switch here, we need to complete the circuit for it to turn on.
Oh, right.
So the power needs to go back. So it's actually, we're running the hot wire here, the hot line, and this is this whole wire here, as well as this filament, and go down here, it's what they call, it's electrified.
Okay.
So it's wanting to get, it's like a hot wire. It's ready to get back to its source. It's wanting to get back really bad, but it can't because there's no connection there.
Oh, okay.
So it's electrified. That's what it's called if something is hot.
Okay.
Or but it's not on until we connect this wire, this white wire, back to our white bus bar, and then you have a complete circuit. Our light will turn on, right? And because this this old light bulb, there's a really small wire in there, so it's actually really hard for the current to go through that wire. It gets really hot, that's why it lights up. But it's really hard for the current to get through. So not very much current can actually make it through that. It's not using a lot of power, not like the microwave. It's just like a really small amount of current can make it through that.
Oh, okay.
We'll just say it uses like 1 amp of current.
Okay.
And this is and most of these breakers on our house, I think they're like 20 amps, most of them. So really, if we can connect a whole bunch of these lights on this same circuit, connect another light, but we want to stay under 20 if they're 1 amp piece, or else the breaker will flip off.
Right.
If
Okay.
we have too many.
So how many amps is like a microwave?
I think like 14 or something.
Oh, okay.
Something around there, 14 amps. But say we're doing construction on the house and we put a nail through here. We hammer a nail in the wall, and it connects this hot and this neutral. So our light, probably is going to go off because all the power is going to come, all the current's going to come through here, through this. It's not a small connection; it's actually a big connection because there's a metal nail.
Yeah.
So current's going to flow really fast through this.
Does that happen a lot where somebody accidentally nails?
Oh yeah, it happens quite a bit. but there's tons of current, and because there's so much current flowing through, it'll actually trip the breaker, and then you'll be safe.
Okay.
So, but if you didn't have that breaker there'd be so much current flowing through this, your wires are going to melt and could cause a fire in your house. So that's why you have the breakers, because that'll trip. But anyways, these breakers, they're not going to prevent you from getting electrocuted. What I'm saying, they're there to protect the wires from melting. They're not going to protect you from getting electrocuted.
Okay.
Unless you have more than 20 amps going through your body, then it could trip. But 1 amp could kill you. So they're not designed to prevent you from getting electrocuted. That's important. Okay, so one other thing here I need to mention is at the light post there is a ground rod, and I think when we go on walks sometimes you can there's a ground rod out here, copper ground rod.
Okay.
With the grid.
Are they usually by a light pole?
The one on our walk, there's one by our light pole.
Oh, okay. But not always.
Yeah. I don't think there's one on every single light pole.
Okay.
But anyways, it is connected to neutral here. So that's the ground rod that's going to be dissipating like lightning strikes and stuff.
Oh, okay.
So that's something important to note here. So say whoever installed this light switch, say this is outside and this is like a metal box here. Say whoever installed this was pulling on the wires, and say there was a really sharp edge along this metal box here. And say that our hot wire was rubbing against the edge of that.
Okay.
So now the box is like electrified, I guess I should say. The neutral wasn't connected. The neutral didn't hit the side of the box. It was just the hot.
Okay.
So that means this box is electrified.
Oh.
And then so this box is trying to get back to its source, right?
Oh.
So say Billy comes along and he's going to change the light bulb. Okay. So he's outside. He's going to go change the light bulb. He goes up and he touches this. This power is going to come through him. Say he's on like wet grass, whatever. There's not a lot of resistance here. It's going to come through him. It's going to go into the ground, and then it will go back to this ground rod, which is connected to the neutral. So it'll make a loop right here.
Because the electricity wants to travel somewhere.
Yeah, it wants to travel back to its source.
But he would be inside, right? If he's changing the light bulb.
I'll say it's an outside light.
Okay.
Or say he's standing in a tub or something. Or say he's in the kitchen or in the bathroom, and there's a sink here. Water pipes that will go into the ground. Say he's somewhere near metal, and the metal's going into the ground, so he's touching this. And he's inside, so power is going to go through him, through here, into the metal. The metal goes into the ground, and from here, it can travel through the ground. There's going to be a lot of resistance through the ground because it's a long path, but there is still power still can make it through. If you know how much resistance you have, like on this light bulb, you can know how much current's going to go through that. There's like some equations.
And so that current will go through the ground over to the ground rod, and then continually keep working.
Yeah.
Until he moves his hand from that.
Yeah. So there's another YouTube channel called Engineering Mindset. And they said, say he's standing in water without shoes on. They said in this scenario, this guy is going to die. He's going to be, I think they said, most likely is going to kill him.
Oh, really?
This specific scenario.
Wow.
So that's what they say. That's what they said.
So that wire that was touching that metal on the light bulb, do electricians have safety features to avoid that from happening, right? If it's installed correctly?
Yes.
So when would that happen? If someone who was an electrician installed it, or it was just poorly installed?
Yeah, if someone that is an electrician didn't install this properly. But there's safety measures in. So anytime we see something that's electrified, whether it's, say there's a a wire running next to this metal pipe here, anything that's metal could be electrified. So he was pulling the wire next to this pipe, and the hot wire came in contact with the pipe. The pipe is now electrified. Also, the faucet is electrified. Whatever. But anyways, so anytime something becomes electrified, we want to know about it right away.
Yeah.
We want that to never happen. If it does, really we want the breaker to flip if it ever happens. But the problem is, here in this scenario, when the power is going back to the ground rod, it's not going to trip because we don't have enough current flowing through our body to trip it in this scenario.
Well, that's scary.
Yeah. But in order to clear the fault and make it so this is not electrified, we have what's called a ground wire.
Okay.
Usually it's like a bare copper wire, and so there's a bus bar here with all the ground wires. This one is connected to the frame of the breaker panel here. But anyways, you connect the ground rod, or the ground wire is connected to the metal frame of this, and it'll come back here, connect into this ground bus bar here. And then this bus bar is connected to earth ground here, and then the wire is connected here. So a lot of people have the misconception that if the hot will ever touches the box, the current will travel through here and go right into the ground, and that'll be enough current that it will trip it. So that's inaccurate. This is false. This will not trip the ground.
Because it's not enough amps.
Yeah, it's not enough amps. Remember, we got this resistance. You can have some current go over here, but it's kind of a similar situation where you're losing some current. It's not going to be enough to trip this. There's so much resistance here. So what you want to do is we want to have what's called a ground neutral connection, or a ground neutral bond. So we have a wire here. Will connect from here to here. So this will make sure that if the hot ever touches the side of the metal box, there will be tons of current that'll come through here, go through this, and go back to your home. Go back to its home, and there'll be really low resistance. So that means there'll be tons of current that'll flow through this loop, and then it'll cause the breaker to trip.
Oh, okay.
So then that'll clear out the fault. If it ever touches the side of the metal box, tons of current will go, it'll clear the fault, the breaker will trip, and it'll clear the ground fault there.
Okay. So that's basically the setup for every single breaker in the home? Like it's set up that way?
Yeah. For the 120 volt circuits, there's a hot, there's a neutral, and then there's also like this bare copper wire that goes back to this bus bar here.
Okay.
Or anything metal in your house, you want them all to be connected to ground. You want all your metal parts in your house, or say you have a metal building, anything metal like the frame of your oven, electric oven, you want that to be connected to the ground, because anything can get electrified in theory, right? If it's metal. And so anytime something gets electrified, you want that to be cleared really fast.
Yeah.
Or else you're going to get shocked.
Makes sense.
So under normal operating conditions, current never will flow through through the bare copper wires.
Oh, okay. But they're just basically a safety precaution.
Yeah.
But you have to have them. Is that standard protocol for electricians, that they have to install those?
Oh, the ground wire? Yeah.
Okay.
Yeah. So, so every single outlet has, grounds. And when you plug your vacuum into the wall, it has the bottom part is the ground.
Oh, so that's what that is?
Yeah.
Oh.
Yeah. So say when you plug your vacuum into the wall, say like part of the hot touches the frame of the vacuum and it electrifies it.
Yeah.
That should trip the breaker,
because the frame of the vacuum is now connected to this.
Oh. So how come there's outlets that don't have that third prong?
They're not as safe.
Oh.
Yeah. Yeah. So that's pretty much why you have your ground. That's why you have a ground neutral bond here, so power can easily go back to its home.
Okay.
And then if there's a short circuit, say the hot connects to here, that's called a short circuit. This is when it connects to the ground. It's when that hot connects to like the frame of something. It's called a ground fault.
Okay.
Let's see. So what other questions do you have?
So I understand.
Hopefully that.
That gives me a basic understanding of how electricity is set up in a home. So as a person who doesn't understand who doesn't know anything about electricity really, except for what you just taught me, how would I go about my home making sure that it's safe?
So I'm going to have a little series on. So I'm going to cover two things in this video. After we're done, I'm going to show you what. Like we didn't have a good ground neutral bond in our house. I'll show you where that is. So see this ground connection? If that's somehow broken, you're not going to be safe anymore. So first off, you want a ground neutral bond, and then you want a good connection to the ground neutral bond. Like this wire here is really important where it connects.
So you can check things like that.
Yeah. So in electrical, in code in the United States at least, you want this connection to be on the first means of disconnecting power on your house.
Oh, okay.
So right now we have a breaker box on the side of our house, right? Where we shut things off. Some people don't have it; they only have it right here.
Oh, okay.
So if you only have this connection, if you only have this shut off switch, you want to make sure your ground neutral bond is connected. In that, you want to go look at your breaker panel and make sure you have a good connection there.
Oh, okay.
And then sometimes there's a screw that will connect this, the neutrals. It'll connect it to like the frame. There'll be a
Okay.
screw, like a green screw, will connect it, grounding screw. Yeah, in our case we have our ground neutral bond needed to be on our main shut off switch on the outside. And it wasn't there.
Oh.
Right.
Yeah. And so that causes all kinds of problems.
Yeah. So in our case, we've got a copper wire that should go out to this metal box here. Because this is, in our home, this is where we do have this bus bar here still. But in our home, we should have, this is our shut off switch. We should have the, the connection here. And we actually didn't have this copper wire to connect all the grounds together.
It wasn't there.
No, it wasn't there. Well, basically, there's a metal pipe that connects from here, from this box over into this box. So they were using the metal pipe as the ground.
Oh,
so instead
yeah.
of the pipe.
Okay.
Now, that in code you can't actually do that. You can use the metal pipe as the grounding conductor. But I was looking at our metal pipes in where it goes over in our attic, and the metal pipes were like, the connection was actually kind of loose.
Oh.
So it wasn't even that great of a connection.
Oh.
Yeah, it was really
That's
loose.
scary.
So I ended up running this wire here, a copper wire, and I'll show you this actually. Will go from this bus bar over into our outside disconnect.
Okay.
And so we have a meter on the outside of our house as well, right? And it's locked, so I can't go in there and look. But I disconnected all the wires, and we did have a ground neutral bond in the meter.
Oh,
I think it was a good connection. It appeared to be, but I couldn't look in there and see it.
Oh.
And I think most meters have that. Some of them, I don't install electric meters. That's the utility company. So it probably depends on your utility company if there's going to be a connection there.
Yeah.
I think most of them have it, but
Who knows?
it may not be that great of a connection,
Yeah.
or may not even be there at all. So that's why they say the code says you need to make a ground neutral bond in the first means of disconnecting power to your house. So but then also you got to make sure you have in each outlet or box in your house, you got to make sure that you have the ground connection, because you could have say he forgot to put this ground connection in here, that could still be electrified.
Oh, yeah.
So, or like say instead of a light, say it's an outlet that's outside, you can put this in your outlets, and I'm gonna have another video on like testing your outlets.
Okay.
And then you're only supposed to have one connection in your house for the ground neutral bond. Some houses have multiple. We had multiple in our house. So that means the power was actually running, instead of running through the neutral, it could run through the bare copper wires throughout our house as well. The power.
Wow.
So so in the future, there's going to be like a little playlist of how to troubleshoot this, making sure you only have one ground neutral bond in future videos, and also making how to test your outlets and use this tool.
That's cool. I didn't know you could test it.
They have a tool. And also you can have GFCI breakers, and also in your kitchen, you know, those buttons that you push.
Oh yeah, like in the bathroom.
So that those ensure that power is only coming in here and going out through the blue.
Oh yeah.
And it'll measure that. If there's power that's leaking out through your feet or through the ground, it'll detect that, oh, there's something leaking out. There's power leaking somewhere.
And it will trip.
So then it'll trip really fast. So the GFCI, those ones are meant to protect you from getting electrocuted, and not necessarily these breakers.
Oh. Oh, that's cool. A lot of stuff I didn't know.
Yeah. So yeah, what other questions you got?
I think that's it.
So yeah, I'll show you the breaker box we have out here now.
Okay.
So yeah, getting electrocuted, having power come through you and through the ground and back to its source, it's actually a pretty serious thing. It can kill you. And so I actually went out near our solar panels. We have a ground rod, and right now this ground rod is not connected to anything. It's not connected to any wires. It's just going 6 feet into the ground.
Oh, okay.
And so I went out there, and I, just like this morning when you were gone, I ran a extension cord. I plugged in an extension cord and into the side, and so essentially I was running the hot all the way over here, way out to the backyard. It's like 100 feet or so. And I measured with my meter. I put one end of my meter on this hot wire and the other one on this ground rod, and I was showing 120 volts.
Oh, really?
Yeah. And then, so I was trying to measure the resistance from like, you know, I had the neutral as well, or the ground. I was trying to measure with this ground on this cord, this extension cord connects to this ground, right? Well, this ground is actually closer. So I was trying to measure the resistance between, you know, this rod and the ground. So I was measuring this resistance. I was having a hard time getting a good measurement for that. But I touched this hot wire. I was being really careful. I touched this hot wire onto the copper rod, and I was getting like 6 or 7 amps of current flowing.
Oh, really?
Through, over here, and then it was going bad. So even though this wasn't connected to anything,
It was
6 amps was going through the earth, 6 or 7 amps.
Oh, wow. So
if that was,
that's a lot that's still traveling through.
yeah, it was like, you know, like sparking a little bit,
Oh.
and like burning the connector. Whereas,
Oh.
so that's like,
kind of scary.
if that 6 or 7 amps was flowing through at like 120 volts, that's like, you know, half of a microwave running. It's like,
Yeah, that's a lot.
so if we were to keep that connected, you know, our power bill would go really high, because all that power
It's just constantly.
we'd be paying for it, you know.
Wow.
It's like we having our microwave running 12 hours a day.
Yeah.
If that connection was there.
Oh, wow.
So-
Interesting.
Yeah, so I touched it and it was, you know, in that loop. I
Huh.
was really careful.
Yeah.
You know?
Yeah, you don't
But,
want to get electrocuted.
Yeah, but yeah, it made the loop.
Huh.
So,
Wow.
yeah, so let's go out and look at the outside connection.
Okay.
So one other thing I didn't explain is power that comes from the grid. Yeah, there's more wires. There's like an extra one here. So you have your hot, your neutral, and another hot. So if you use your electric meter to measure from here to here, 120 volts. From here to here, you get 240 volts. I don't know if that makes sense. But
Okay. Yeah.
yeah, so there's 3 wires.
Okay.
And here on our electrical panel, you can see, so yeah, that bus bar behind there, that's actually not touching, you know, it's going behind, and it's not touching the frame of breaker box, if you notice that.
Oh, okay.
And then you have all your copper grounds connected to a copper bus bar over there.
Oh,
And you notice
Okay.
there's no connection between the two right here.
yeah.
There's no connection. But that's all the circuits.
Cool.
So if we go out here to our main disconnect, here's our meter. And see this shiny copper wire?
Mm-hmm.
I added this. So there's you can see here there's yeah, careful, this is all hot. But
Oh, okay.
see there's 2 hots in there.
Uh-huh.
And then the one with white tape, that's the neutral. Because
Oh.
it didn't come with white, so the electrician when he installed, you know, that tape's like 40 years old.
Oh.
However old our house is. Yeah. But yeah, and then the copper goes in here, and then it goes into our meter, and then in our case it goes down into the ground, solid copper, and then I believe that goes into a grounding rod.
Oh, wow.
I need to verify that is a good ground, but anyways, here's where I'm connecting the neutral, the ground, and the neutral,
Oh, okay.
and then that wire in the back goes all the way over to the other panel, and then this connects here to that.
Wow.
Yeah, so I do have 2 coppers going into the one terminal there. That's not the best practice, but so I could have put a bus bar in here, but I didn't feel super comfortable reaching in there and putting a bus bar, because even though I turn it off, I still have like live power
Oh, yeah.
in this box. No matter what,
So you
there's
just
live
want it
power.
to play it safe.
So yeah, and really the copper that I have connected, it's just extra. I don't need it, but it's extra just in case the ground connection came loose, because before it was only the ground was like that little one
Uh-huh.
connected to the frame, and then this frame was connected to the frame of the other one by means of a metal pipe.
Oh,
So
right.
the metal pipe was the ground.
Oh, right. So it's just safer now, basically.
Yeah. So.
Huh.
So yeah.
Good job. That looks difficult.
So that's that. So we'll have another video on explaining making sure your electrical appliances are safe shortly here, or like electrical outlets, and also testing the ground neutral bonds and some other items in that other video. So let me know what you guys think. If I missed something, talk to you later.